So the plan for today is to go a little bit over time. Let's make a break. Let's take a break in the middle, but we'll try to catch up with. Can I also go a little bit over time tomorrow? Is it okay? So that in total we compensate for this lecture. Okay. So then, if everyone is okay, we'll go an hour and a half today and an hour and a half tomorrow, and then we'll recover the missing hour in this morning. Okay. So let me first review a couple of basic points that of things we have seen so far in the lectures. So one thing we saw was that we might have a theory that could be free, where we have, say, a free scalar, and we consider an operator of dimension, classical dimension 2 at point x, classical dimension 2 at point y. Then classically, free theory, it will be just two propagators from x to y, so 1 over x minus y to the power 4. But then quantum mechanically, we start getting some divergences we need to regulate. We get some logarithms. And those logarithms, the interpretation is that I can define a renormalized operator, which is basically this operator is just my bare operator, phi square of x times epsilon to some power depending on the divergence that I got. So I absorb this dimension into my bare operator. Now I have some renormalized operator, which has two-point function, 1 divided by the distance to a number that is now no longer just a classical dimension, which was 2, but got some quantum part. Okay, this would be what we would get in some phi to the 4 like theory in 4 dimensions. We also saw that some theories are not conformal. Most theories are not conformal. One thing that happens is that we start with a theory with some coupling, and that coupling depends on the scale you are, depends on the cutoff, it depends on the scale. And so as we integrate out stuff, we get some effective couplings that are the original coupling plus some logs. Right? And one way of interpreting this is by saying that this object here, this operator, this is an operator, this is another operator. By this, I mean the full thing, not f. The full thing is an operator. And normally, this operator would have dimension 4, and this one would have dimension 2. Right? And if their dimension was quantum mechanically 4 and 2, then this Lagrangian would be just invariant under scales. There would be nothing. And you would never generate logs. So another way of saying that we got a beta function is equivalent to saying that these operators acquired some quantum dimension. And therefore, the theory, these Lagrangians, they are no longer objects of dimension 2 and 4. And therefore, the theory is not quantum mechanically conformal, although it is classically conformal. At the classical level, these Lagrangians have no scale, right? G is dimensionless, and it looks like everything is dimensionless, right? But then, quantum mechanically, these operators actually are not really precisely of dimension d. They acquire dimension, and the theory is not conformal. The beta function very explicitly had this very important minus sign that was asymptotic freedom, and it was given by minus 11 over 3 times n squared times g Young-Mills cube. And that led us to think that this combination should have a good large n limit, should be a good limit when n goes to infinity. That is, you take n to infinity coupling to 0 with a product fixed. Because then this equation was invariant, right? On the right-hand side, you had dg d lambda, and you multiply by n's with the right powers, and you see that you get a nice differential equation for lambda without any powers of n. And indeed, then we went to analyze matrix models that precisely proved or backed up this intuition and showed that indeed the 't Hooft limit is what you should do, and if you want to have a large n limit. And if you do diagrams that are planar, that can be drawn on the plane, such as this one in matrix models, they dominate in the large n limit. And this would be a diagram, for example, if I put a trace of m here at some point, and another trace of m, quote unquote, at infinity. This would be this dashed line at the very end. And then this is the cylinder, right? There is a circle here, there is a circle at infinity. I would draw this diagram on the cylinder. It was the same type of diagram I was drawing last time. And this looks like the triangulation of a closed string. So this picture looks like I have a closed string that propagates, and the various shapes of this closed string, the integration over these possible shapes, would be the summation over these possible diagrams. Here I would have trace of m to the 7, trace of m to the 7 at infinity. Okay. Many of these things that we discussed before will show up today and tomorrow. Now, today and tomorrow, for the most part, or at least today definitely, for a full lecture, I will be following a nice review by Joe Minahan, and you got a paper which has basically the main formulae that we are going to go over, so that I don't need to write all these formulas with all these indices, neither do you. Does everyone have one copy? Yeah? Okay, so some of these things are review, or I should assume that people know, like the first formulas in 1.1. Now, what is one? So let's go over this page and see what is. So first we start with the conformal algebra here, which is just the algebra of transformations that we get if we associate each transformation to a conformal transformation, right? So we have dilatations, rotations, and so on. So let's look at this equation 1.1, and can someone tell me something interesting about the first equation? Maybe let me try. We have enough equations for everyone. Let me start. Let's put Ami on the spot. Tell me something about the first equation.
Dilation and momentum.
Good. The first equation tells dilation and momentum, they commute to give back momentum.
It kind of makes sense that they do not commute, because if I imagine I have something in the center, I translate and dilate, and then I translate back.
Yeah.
It goes somewhere else, right?
Good.
So they don't commute.
That's a good. That's good. So they shouldn't commute, indeed. What would you? So good. Now, what's your name? Nearby me? Marcelo. What would you say comparing the first equation and the third equation? What's the main difference between the first equation and the third equation? Yeah. That's the dilatation with P versus dilatation with special conformal, right?
Yeah, it's just a minus sign. So
Just a minus sign. What would be the interpretation of this minus sign?
it's related to creation and annihilation operators.
That will be, but what about from the point of view of what Ami just said? Would you be able to?
What is it?
That if you make a dilatation and then translate, it's not the same as translating first and then making a dilatation, right?
Okay, it'll be when you inverse, you also inverse the dilatation. So
Very good. Very good. In other words, dilatations, they increase sizes, and under inversions, right? So if I increase some size here, I'm squeezing it at infinity. Likewise, if I'm increasing at infinity, I'm shrinking here. In other words, 0 and infinity are related to conjugation by this operation of inversion. And inversion is what flips precisely momentum and k, by definition, right? And so it's natural to have this sign. Now, what else could we tell about the first and the third equation? What else would be useful to know about the first and the third equation? Which tells us how the dilatation commutes with D and how something commutes. So how do we use this commutation, for example, of the Hamiltonian with the creation operators of an harmonic oscillator, right? So let's follow that analogy and say something about the first and third equation. Now, Manu.
P becomes our Hamiltonian.
Right.
So P will be either raising, lowering, K will be the opposite.
That's right. So to see, so the point is that the Hamiltonian, what happens is that if you see in equation 1.3, he works out in detail that the dilatation operator acting on an operator that was acted upon by K gives delta minus 1 times that operator. So K lowers the dimension by 1 and P increases the dimension by 1. That makes sense, right? Because why does it make sense that P increases by 1? So let's go next one. So here, sorry, your name? Carolini. Why is it intuitive that P increases the dimension by 1?
I find it intuitive though.
What is P? What is the translation operator? How do we do a translation? You have O at the origin, and you remember what were the descendants that was acting on with P? So O at the origin is O, and then the next term was when you have the descendants, right? All these towers of descendants. The derivatives, right? And what does a derivative do with respect to dimension? Increase by 1. And remember, what was k? K was something that was not the derivative. And k is conjugate of p. So k is like removing derivatives instead of putting. All right? And so let's see if that makes sense, that k and p act, one puts, one removes. Let's look at the last equation in the first line. Right? What does it tell us? It tells us that p and k, indeed, when you commute them, right? We don't get exactly one, but we get something that is neutral, right? That just measures the dimension or rotates the operator, right? And so it's the analog of a dagger a equal 1, the commutator. So indeed, one adds dimension, the other adds to remove. Now next, here in line. What would you say about the second equation? D with m mu nu equals 0.
M is
M, what generator would it be of the conformal algebra? We already have translation, special conformal, dilatations. What's the remaining transformation? Rotation. And so what would this equation tell you?
This doesn't matter.
Exactly.
Which order we-
Right?
Dilatations or rotations.
Exactly. That doesn't matter, right? So if we make a dilatation and then rotate, or if we first rotate and make a dilatation, indeed, geometrically, that's the same.
It's Lorentz transformation that by definition non-preserving. M mu nu is the
M mu nu are the rotations. And so these rotations, right?
It also contains the boosts. I'm saying Lorentz transformation automatically fixes the magnitude. So that's why
Here we are doing Euclidean. There are no boosts.
okay.
Here we only have rotations, translations, special conformal, and dilatations. And rotations indeed doesn't matter. I can rotate and dilate, or first dilate and then rotate. It's obviously the same thing. What about from the point of view next here? What's your name? In purple? Not exactly purple, something. Satiris. What would you say about the second equation? Not from the point of view of geometry, of commuting or not, but more from the point of view, the same type of analysis we did for P and K with respect to increasing and raising dimension.
Rotation does not raise the dimension.
Yeah.
With the dilatations.
That's right. So if you have an operator and you rotate the operator, you get an operator of the same dimension. Right? If they are scalar, it's obvious. If they are scalar, they are killed by rotations. Right? That's phi squared, doesn't care about orientation. Anna and Charlie, you both can tell us about the last two equations.
All right.
These are two equations, of course. There is a comma missing.
I mean, would you construct them by a symmetry argument?
Yeah, that's right. In other words, what is this equation? How does?
Says that momentum is a vector.
Precisely. It just says that the first equation says momentum is a vector, and therefore momentum commutes with m in that way. And now that you know this, how should it? What should it give with k? Same thing, right? K is also a vector, and indeed, you see the last two equations are the same if you replace p by k. Right? By the way, there is one that was not written here, which was m with m. Right? By the same logic, what's your name?
Jaime.
Jaime?
Yeah.
Jaime. How many terms with m have on the right-hand side? This guy has two terms, right? These two equations has two terms. M with m. How many terms would we have on the right-hand side?
There's 4.
Exactly. Why?
Well, because it's how a two-tensor arrives.
It's how a two-tensor will transform, right? So m commutes with any tensor, transforms either the first index or the second index. And so it's like two vectors transforming. So we would get 4 terms. Very good. Okay, then we have these primaries and so on. So 1.1 up to 1.3 is done. And that's all for now. Let's postpone a little bit the remaining equations. Okay, so now we'll switch gears and we'll come back to the conformal algebra. We'll generalize it to a super conformal algebra when we will have the conformal algebra plus supersymmetry. when we find a theory that I will tell you is superconformal. Then it's interesting to ask, what is the superconformal algebra? Okay. Now, first, let's suppose I have a D-brane in string theory. A D-brane is a plane, a hyperplane, where strings end. So there is an open string, and the endpoints of open strings, they need to end on D-branes. That's what a D-brane is. Now, this D-brane can be space-filling, in which case it means that it's a 10-dimensional plane, 9 plus 1-dimensional plane. Then it would be called a D9 brane. This 9 is just 10 minus 1. It's just saying that it occupies all 9 dimensions plus time. So it's really space-filling. And now we have this D-brane where the strings can end. And what I want to ask is, what is the theory that describes the low energy limit of this 10-dimensional theory? Or more precisely, what I want to imagine is that I have maybe not one brane, but maybe a stack of branes. A stack, right? Like a deck of branes. And there are n of them. Capital N of them. They're on the same position. Well, in this case, of course, they're in the same position because the brane occupies all space, so there's not much room. So they are both, all of them would be space filling. There are n of them. And the open string ends on the brane and goes to the brane. And we ask, what's the low energy limit? What happens if I go to low energy? What describes this? What is the low energy description of this theory? Well, what's the answer? The answer is that we get a theory in 10 dimensions because we are doing 10-dimensional string theory. Right? And what are the lowest, what are the massless modes of open strings? At very low energy, what do these strings describe? Photons, or in this case, when we will have indices, we will see that this would be gluons, and so this would be 10-dimensional super Yang-Mills theory. And what happens is that at low energy, if I have low energy, the string is effectively very small because the tension of the string is much bigger than the energy of the string. And so the string effectively becomes very small, right? Because I have some tension. That's if the energy is so big, the string becomes big, and I would see it. But as soon as the tension is much bigger, if I'm at low energy, the string is very small. So it will be a very small string. So this is a particle from far away. And this particle is the gluon at low energy. Plus, because the theory has supersymmetry, plus the psi, the supersymmetric partner, that you will see in a second. And this will be the massless particles that will describe, that will be the low energy limit. Now, let's see how to draw the story of some strings moving in this D3 brane. So let's suppose, let's follow the life of a string moving on this D3 brane, so this D9 brane. So there is a string, here it is, that is like this. And then it evolves in time, time goes up. So the string started like this, and then moves to this, and now is moving like this. I'm drawing a story of the string. The string is moving in time and it's doing this. Now, at some point, it could even do something like this. And at this point, this middle point of the string is touching the brane. It could decide to open into two, to split into two. At this point, the string could split into two strings. Then they can propagate a bit. They can go away from each other, these two strings. Then we continue here. They would be here. Then they could join. They could approach each other again. Eventually, they would be so close that they could reconnect again. And then after reconnecting, it could go up and move and then continue happily forever. Well, this would be a story of a string, right? This would be time going up and continuing here and continuing here. Now, let's be more specific and say, where are the endpoints of the string? Well, they end up on the D brain, but there are n of them. We said there is a stack of D brains, right? So let's say that this endpoint is on D brain I, and this endpoint is on D brain J. And they continue. And so this endpoint is in I, this endpoint is in J. This endpoint is in I, this endpoint is in J. I'm going to be tired of this. This endpoint is in I, this endpoint is in J. This endpoint is in I, this endpoint is in J. But now when they reconnect here, where do they do it? Well, they go down, right? And they touch a D brain and split, but which D brain? I or J or what? K, right? It will be any of the D brains, K. So this would be K, but this one is also K. They touch the same D brain, right? And they split. Very important, the same D brain. So K, 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 and the same I and J. And so the picture that we have in space-time is this. You have your string coming. These are the two endpoints of the string. Then they split into two. And here there is a new index K. Here there is I, and here there is J. But this is familiar, right? This is nothing but these fat diagrams that we were drawing before. And now at the end, this K annihilates and the string goes on. And so this picture, we recover again precisely our fat Feynman diagrams. Or ribbon Feynman diagrams. Now, you could imagine more complicated configurations where the string splits into three that reconnect. And there you have planar and non-planar. Right? Reconnections. You have the planar one that dominates and the non-planar one. And in this picture, we can draw it here. So we could imagine this situation where now I have a string that splits into three, like these diagrams we were drawing. These ones were proportional to n cubed. Versus we have this other one where the line connects like this, which is non-planar. And you can try to draw what's the story of, this one is obvious, right? I'm not going to draw, but what's the story of this string here? It will be something like this. Let me see if I can draw a reasonable story. So there is one string that first splits into three. So when it splits into three, the string goes from here to here. Right? These are the endpoints. And now new endpoints form here, right? So here we'll open up and we get here, and here new endpoints form and we get this. So now we have three strings. Do you agree? But now, normally, let's put the index. This is I, this is J, these guys are K, and these ones are L. This will be the generic thing. This is what we will do here, right? K and L. And then we sum over L, we sum over K, and we get this n squared that dominate over here, where here you see that this index here, if this is J, let's color J in red. You see that this J, if you color it, it's the full interior. There's no room for anyone. You see, you color with red and you get the full thing. So there is J and there is I here in this picture, no one else. Whereas here, you have room for a different brain here, K, and a different brain. I don't have more colors. And a different brain here, L. So let's see what happened there. How did we lose this? How did we lose this option of coloring? So here we create these strings. And now, after we create these strings, we have this, this, and this. Okay. But now let's color in orange the last one that starts here at J. I'm coloring just to indicate, to remember who starts at J. And now they are here, the three of them, and let me continue the story here where they swap places. This guy and this guy here. So this is J. Okay. This one here was I all the time, and this was I. And now, these guys, at the end, I want to reconnect to make my string again. So now the goal is to reconnect this and get I here, a reconnected string, and J here. Do you agree? Good. So then how could this reconnect into this? So now let's work backwards. How could this happen? So first of all, I want the last endpoint to be at J. So it means that here I need J. Do you agree? I need these two to be able to reconnect. So it means here I also need J, because J can reconnect only with J. And this endpoint was the same as this. They came from here, from opening here. Right? And so this guy also needs to be J. And they need to reconnect. So this one needs to be J as well. And so indeed, everyone needs to be J, which is exactly the picture there. And so what we conclude is that these fat-Witten diagrams, they also describe the propagation of open strings. And you can think of these diagrams as literally the open string propagating and splitting and so on. And so we have this new way of thinking about these diagrams, that these diagrams, they look like they are describing open strings. Yeah.
So I understand like why does it's J kind of everywhere in that one, but in the first diagram,
Here?
like, here you have like a 4 vertex, right? Kind of. So for
Yeah.
it to be all the same instead of like.
But let's see the index, right? This index is I, this is J, this is J, this is I, this is I, right? So if I go around this vertex, the vertex says is JJ, LL, KK, II. Right? Remember, the quartic vertex doesn't fix all the indices to be the same. It just tells you that it's a matrix multiplied 4 times. Remember? Right, so the vertex was this, right? The only thing the vertex, what is this notation telling? It's telling you that this index is the same as this. And then this is the same as this. And then this is the same as this. And then this is the same as this. We opened it precisely to remember which indices are identified. Precisely not to think that all of them are identified, but exactly to tell us how to identify the indices, right? And the indices are identified according to matrix multiplication. Right? And so we see that we have here open strings. But the first time we found these diagrams, we were discussing more like closed strings, right? We had a closed string, trace of M, and then we had some propagation. And what we are starting to see here is the tip of the iceberg of what is called open-closed duality, which is often, whether you are describing open or closed strings, depends on your point of view, your taste. Let me give you a very simple example. Suppose I have a D brane, and I have an open string that is stretched from one D brane to another. Here is the open string, right? It's an open string stretching from this brane to this brane. Okay, a string that ends on one D brane and ends on this D brane, right? If I put the stack on top of each other, it would be like one of these strings that we were drawing. And now, take this string and carry it around to make a circle. Take this endpoint and carry this endpoint. And so you get a cylinder like this. And so you see that from this point of view, it's an open string. I take the open string and I carry the open string around. But if I tilt my head and look at the picture from this point of view, it's a closed string. Right? If I cut the string here, it's a closed string that is propagating from one end to the other. So the very same diagram we can understand as either a closed string or an open string. And that's the same thing here. This diagram here, I can think of them as an open string that is moving around. Another way of thinking is that this orange line is a closed string. And this red line is also a closed string. And so what do I have? I have an open string that interacted with two closed strings. And so another way of thinking is that the D brane is a source of closed strings that is constantly sending closed strings. And then this open string is propagating, interacting with these closed strings. And so either I think of the open string just propagating and splitting and so on, or equivalently, I can think that this open string is described, also sees closed strings. Let's draw a picture just to see that. It's becoming a detour, but I think it's an interesting one, so it's okay. Suppose I have indeed, let's draw a 3D shape that draws what that process is. Or maybe just the first one. The first one is easier. So I have a closed string. I have an open string that's propagating, right? And then it's splitting into two. Right? And so I have this picture where here, if I draw it in 3D, there is these endpoints are on the D brane. And here, these endpoints are on the D brane, like this one were. And then they join again, and I end up here with the closed string at the end, with the open string at the end, right? Do you see this picture? It is just that in 3D. And now you see that that is true. I get these open strings. But if I think from this point of view, yeah, it's really seeing it from that. There's a string there. So if I cut it here, I follow here. Here I could say I have a closed string. Right? And so here I could think that from the top, that what I have is I have a closed string that wants to be emitted from the brane and propagate inwards until it's the smallest possible. Right? The closed string comes from here until the smallest possible, except that, okay, it's hit by an open string here and here. Okay, there is some interaction with the open string at the ends, here and here. Otherwise, it's like really a closed string that is evolving, and it's just looking it radially instead of looking it sideways. Okay, we'll come back to this open-closed duality later, but for now, we see that the low energy limit that normally as someone said, would be photons. Because we have these d-branes, we get for free this all these non-abelian Feynman diagrams. So what we get is not an abelian theory of photons of a super QED, but really a non-abelian theory, which would be super Yang-Mills instead. So what is this theory then? This theory, the Lagrangian for this theory is, well, there is the usual 1 over g squared integral. We are in 10 dimensions, so d 10x. Then there is, I think conventional, if we put a 1/2, then there will be 1/2 of trace of f m n squared, where m takes values from 0 to 9.
Pedro, can you just raise the middle blackboard a bit so that there's no shadow?
This would be just pure Yang-Mills. Am I normalizing it properly? Sure, I had written it here somewhere, but I forgot where it is. Yeah, it's okay. Plus, and then superstring, there are bosonic and fermionic degrees of freedom. The Fermion ones would be trace of psi, gamma, m, psi a, gamma m, a b, d m, psi, b. And this would be the low energy limit that we would get if we put this theory, the superstring theory, type 2b superstring theory, on this D9 branes. Now, our goal is to start with this theory. And this theory is not perfect for many reasons, but one of them is that in this theory, when we are in very high dimensions, this coupling is not dimensionless. This theory is not even classically conformal because this coupling has dimension in this case. And so what we are going to do is take this theory and we are going to dimensionally reduce it. We are going to say that these 10 dimensions are equal to 4 dimensions plus 6 dimensions. And we are going to say that nothing happens in 6 dimensions. And we use this theory as a trick to generate a theory in 4 dimensions, like this. Because this theory started with a mother theory, which was a low energy limit of a string theory, this theory acquires many symmetries that comes from the mother theory. And so this theory is very symmetric. And this theory that we will encounter will be what's called n equals 4. It's this, I will say what this is, supersymmetric Yang-Mills theory. And the idea is that this theory is conformal. This is a conformal theory. And this theory has lots of supersymmetry. And supersymmetry are transformations that I will write that leave the action invariant. And that's what the remaining equations that are written in those pages. But first, before we go here, so this is where we want to go, we have to first understand this equation, understand this Lagrangian in more detail, understand the notation in more detail, and understand how to do this reduction in more detail. So that's what we are going to do now. So let's continue decoding the various building blocks here. This M is a 10-dimensional index. This is a spinor. So this takes values from 1 to 16 in 10 dimensions. It's a real spinner. And then these guys are the usual gamma matrices, but in 10 dimensions. Right? So you are used to gamma matrices in 2 dimensions and in 4 dimensions. In 10 dimensions, there are some bigger matrices that obey a similar algebra. Right? That if you multiply them, gamma m, gamma n, you consider the symmetric combination. This is something like eta mn. Right, so these are 10-dimensional gamma matrices. And all these fields are matrices. They are all matrices. So here, A mu, like we said before, is an n times n matrix. So is psi. This psi A is also an n by n matrix, transforming in the adjoint in the gauge group. And so this derivative here, what this derivative does, what this derivative is, it's defined as derivative with respect to m of psi plus I g commutator of A m with psi b. Or any field. You just replace the field, you put it here. That's how the covariant derivative acts.
Usually in the Yang-Mills theory, if we have the coupling in front, then the covariant derivative has no factor of the coupling.
Good point. Great comment. Indeed, if I put the coupling there, I should not put it here. So let me remove. Thank you. Good point. Indeed. Or indeed, what I often do is I absorb the coupling, remove the coupling from here and put it in front. But since I wrote like this, it's better to remove from there. Okay, any question about the definition of this Lagrangian? So far, I just defined some symbols, and these are gamma functions in 10 dimensions. This is a spinner, a real chiral spinner. There are 16 real components. This F mu nu is just the commutator of these covariant derivatives, right? dm, dn, where these act like that. And that's it. Now,
How do we get the number 16 in that case? That's
this 16 is 2 to the 10 over 2. So if you are in d dimensions, if you have a real spinner, this is the dimension. So let's see. If I put 4 here, I get 4 over 2 is 2, I get 4, right? So that's the number of components of the Dirac equation. And
this becomes 32.
32, good, 32. And then I divide by 2 because I want them to be real and chiral. And so I have an extra while condition on this. Very good. So this is, I want these guys to be real chiral. And this is the usual. Okay. Now, this section is invariant, as I said, super. So it has invariant under transformations that I'm going to write in that blackboard there. I have to erase this. Maybe I can have half an hour more because of that. So supersymmetry is a statement that the Lagrangian goes to Lagrangian plus a total derivative. So it's basically a symmetry. If you transform the fields as follows, if the variation of psi A is equal to something I'm going to write. So you know that supersymmetry flips bosons into fermions and fermions into bosons, right? So we will have variation of psi and variation of the gluon. Right? Now, let's try to guess what these guys could, what they could be. For example, psi. Psi transforms in the adjoint, right? Psi under a gauge transformation transforms with omega psi omega minus 1, right? It's an n by n matrix. So on the right-hand side, we must have the gluon, but as a field strength. If it was just the gluon doesn't transform in the adjoint, right? The gluon transforms as omega gluon omega minus 1 plus some boring term, right? So here I should have something. I want something to write something proper. I want to write Fmn. Now this equation doesn't make much sense, right? Index-wise. So what could I do to try to make something that makes sense? How could I try to take these indices, which are m and n indices, and convert them into spinor indices? What object do I have that has both types of indices? Gamma matrix. So let's write something that would make sense. So I put a gamma matrix to kill the index m. And then let me put this indices a bit later. Still doesn't work. I still have an index n.
One more gamma.
We could put one more gamma. N. Now let's try to see if we can make these indices work. So, I did not tell you, but as usual, we actually have gammas at our disposal. We have gammas and m's, and we also have gammas with upper spinor indices that are defined in a similar way. Like in n equals 4, you can, like in 4 dimensions, you can define sigma with mu downstairs and sigma with mu upstairs. That will be the same thing with the same type of relation, and there is some fierce identity between them. So they both exist in 10D. There we have these matrices. And so here we want an index A, so it's clever to put here AB. Now A is already up here. Then we don't like B, so we could put here BC. Now we kill B, but we still have C, but that's fine. That would be contracted with a spinor epsilon that says that I do a transformation in a direction epsilon C. And this would be the parameter of my superconformal, of my conformal transformation. And then by definition, I'll put a 1/2 that I can absorb in epsilon C if I want. What about A? What about A? Well, A, you can easily see, you want now to put a psi here, a psi B, and now what do? You want AM, so you can put some gamma matrix M. You don't want B, so you put BC. Then you have C, but you have the spinor index. You have the spinor epsilon C, and that's it. And all you need to do now is fix some normalization, and the correct normalization turns out to be IG. So the claim is that if you do this transformation, then the action is just a total derivative. This is the only transformation you could write, which has the proper indices, and indeed this action has this supersymmetry. So this is what's called, in this case, n equals 1 supersymmetry. Okay. Now, let's go to n equals 4. So what we do next is we imagine that now we want to go from 10 dimensions to 4 plus 6 dimensions. Right? And so we want to decompose things according to the 4 dimensions and the remaining 6 dimensions.
Here, why this Lagrangian is the same that Lagrangian, right? Why did we call n is equal to 1 supersymmetry?
I'm just saying these transformations form an algebra that's called n equals 1 supersymmetric algebra. This is the name of the algebra that these transformations generate. Now, how do we go from 10D to 4 plus 6D? So let's start with a simple example. For example, when we have a m, we have to separate this m that runs from 0 up to 9. We separate this index m into mu that runs from 0 up to 3, and say m that runs from 4 up to 9. Okay, but 4 up to 9 is a bit annoying, so let me, once I have m, then I relabel and I say this goes from 1 to 6. When I see an index m, I just shift the indices by 3. So 4 is 1, etc., 9 is 6. And so we can split the index m into an index mu that runs from 0 to 3, and an index m that runs from 1 to 6. Right? Now, once we do it, we say that this field becomes equal, let me use this notation, a mu when we are in the 6th direction, in the first 4 directions. But when we are in the other ones, I call it pi m. Right? Good. Now, you see, why did I call it phi? Because now, if things only depend on 4 dimensions, these other components, they transform as scalars. Right? Remember that under a gauge transformation, am transforms as omega am omega minus 1 plus omega dm of omega minus 1, right? But if we don't allow anything now to depend on the extra 6 dimensions, this is 0 or the index m. When we are in the directions, when we take this index m to be along the last directions, right? And so the last components of the gauge field just transform like this, like a scalar. Like an adjoint field, like the fermion. It's not a connection anymore.
In what cases, if I
Right, so a mu transforms as a mu goes to omega, a mu omega minus 1 plus the usual connection term. But the scalar, phi m, just transforms as omega phi m omega minus 1.
But this is only for some specific omegas, right?
Okay. When omega, that normally would depend on x mu and xm, when we say that nothing depends on xm. Right? There's no dependence on the 6 dimensions. 6 dimensions are empty and everything is in 4 dimensions. So there's no derivatives with respect to xm. Nothing depends on xm and things only depend on 4 dimensions. Indeed, if we write this, what would fmn the trace of f squared, right? What would this fmn become? You see, if both indices are mu, right? Both indices are mu, this becomes just f mu nu, f mu nu, when the indices are in the 4 directions. If the indices are in that one is mu and one is m, we would get plus d mu phi m, d mu phi m. if one index is in the first 4 directions and the other is in the last 6. We would get just this covariant derivative of the scalar. And if both indices are in the direction m and n, we would get plus g squared times the commutator phi m phi n squared from the interaction term. Right? So here we are using that this guy is just the usual thing. dm an minus dn am plus ig commutator of am an. Right? So when the indices are in the directions in the 6 dimensions, this is nothing, and I get just a commutator square. Right? Maybe there is a minus sign, I don't know. And so this is what this term becomes. What about the next term? The other term in the Lagrangian is this psi gamma m dm psi. And now this one, let me write schematically. Schematically, this would be what? This would be something like psi gamma mu d mu psi, where now these guys are 4-dimensional gamma matrices. But if I am in the direction 6, then this derivative is just a Yukawa-like interaction because the derivative does nothing. It's only the commutator that matters. Plus something like psi commutator of phi m with psi with some gamma matrix m, the 6-dimensional part of this gamma matrices here, perhaps some ig. Do you agree? Right? I mean, when it's mu, I just did nothing. When it's m, I just used that the derivative was up there, right? Derivative doesn't do anything, and it's just a commutator, right? But the commutator of am, when m is the 6 dimension, is just the scalar phi. Do you agree? And so what we would get is a funny looking theory where we have some gluons in 4 dimensions. That's okay. So in this theory that we get, there are how many scalars? There are 6 scalars. There are gluons. There is the gluons in 4 dimensions. And there are some fermions with some couplings that are reminiscent of the missing 6 dimensions. There are some gamma matrices here of 6 dimensions that kind of remind us that the mother theory was 10 dimensions. Right? The 6 also do, right? When you see a 6, you think, oh, this 6 probably came from 10 plus. It was what's missing, right? The gluons have 4 dimensions, 6 is 10. So this number 6 also reminds you it came from string theory. But here it's even more explicit. These gamma matrices are the gamma matrices that appear in 6 dimensions. And here you get 4-dimensional gamma matrices. And here it would be roughly 6-dimensional gamma matrices. Now what you should do is you take this spinner that has index A, psi A takes value 1 to 16. And what you want to do is decompose it like we did for the gluon that we wrote, it's a mu plus phi m. You want to decompose it in things that transform properly in 4 dimensions. You agree? So that's a little bit more subtle to do. I'll give you the answer. what it is. And maybe we will take a break, and during the break I will write explicitly this map in more detail. But in what we do is you decompose into psi that you can have Lorentz index alpha. Alpha takes value 1 or 2. And then there is an index A, which takes value 1 to 4. And there are other fermion psi bar that takes index A, the same A, that takes values from 1 to 4, and Lorentz index alpha dot. And alpha dot takes values 1 and 2. So before, so let me just come again, say that all I'm doing here is mu. I'm breaking it into alpha and alpha dot. This is the thing that you must be familiar, right? That if I have a vector v mu, I can construct a vector, an object v alpha alpha dot. How? By just contracting this with the appropriate gamma matrices or sigma matrices, sigma sigma dot. And so this is just decomposing, noticing that SO4 is just SU2 times SU2. And so when you have this mu index from 0 to 3, you can decompose it into 2 spinor indices. And it turns out that for fermions, this is very convenient, as you know.
I got confused by. I think sigma mu should be on this side or something. What is polymatrices? How many index can it have?
Oh, sigma mu. The first one is the identity. The other is sigma x. The other is sigma y. The other is sigma z.
Got it.
And then there is this A that runs from 1 to 4. And this vector, this A here, is the fundamental. This object transforms in the fundamental of SU4. And this A up here means it's the anti-fundamental representation of SU4. And this means it's the 2 of SU2, the spinor of SU2. So who ordered SU4? How could an SU4 suddenly appear? So let me just remind you that you have these 6 scalars. And so this index M takes value 1 to 6, right? This M takes value 1 to 6. And you can say that this is a vector index of SO6, because you have these 6 dimensions and there is a rotation of this SO6. And so right now we have SO6 showing up. That's okay, that's natural. That's just the rotation of the orthogonal directions. We have alpha and alpha dot that are SU2. This is just the decomposition of the Lorentz group. And now I'm saying that this A breaks down into this. Let's first check that the numbers make sense. So there are 16 components. How many components do we have here? 2 times 4, 8, plus 2 times 4, 8. 8 plus 8 is 16. So the decomposition from the number of degrees of freedom, it makes sense. So now I just need to write you a precise equation that shows how this goes. But who ordered this SU4 group? Why would they like to transform nicely under this SU4? What is this SU4 doing here? This fundamental. So you know what SU4 is, right? 4x4 matrices, with unit determinant, etc.
SO6.
Yeah, SU4 is nothing but SO6. SO6 is indeed isomorphic to SU4. It's the same as SU4. And so that's the origin of this SU4. It's the same. It's actually also a sign that there is some 6-dimensional space missing. And you see that now, instead of 1 type of fermions, we have 4 types of fermions. Right? And so when we specify a transformation, we have not only a spinor index, but we can say in this flavor index, where do I go? From 1 up to 4. And so I have more supersymmetry now. I can choose from 1 up to 4. This 4 is the n equals 4 of supersymmetry. So this 4 is this curly n of supersymmetry. And this is actually the maximum supersymmetry you can have in 4 dimensions. It's 4. So this is the theory with the most supersymmetry there is. Okay. So let's take a break. During this break, I will write just for your, in case you are curious, I will just write the decomposition of 10D going to 4D. It's useful to know this reduction of 10D to 4D because 10D no one forgets. I mean, the 10D action is f squared plus psi psi bar, right? I mean, it's impossible to forget the action in 10D, right? If ever you forget the precise couplings in n equals 4 that are many, many terms and so on, coupling the fermions on scalar, just go to 10D and then descend back. Oh, it's useful to know how to descend down. Yes, Anna?
I'm still trying to phrase the question, but yes, the two groups are isomorphic, but
Yeah.
still, is there some difference in the fact that, you know, you get SO6 in the one case and SU4 in the same in the other case? Like, they're still different groups in some sense. So,
No, it's the same group. It is just two different representations of the same group. One is a vector representation, and then I label the scalar by a vector index. The other is a spinor representation, and we label the spinor by a spinor index of SU4. It's like in 4 dimensions, when you have SO4 for the objects that are like vectors, and then for spinors, you typically use as alpha and alpha dot, right? But it's the same thing, and if you want, you could transform everyone to alpha and alpha dot, right? You cannot transform everything to vector indices, but you can transform everything to alpha and alpha dot. And indeed, in a few minutes, we will end up transforming everything to SU4. And we will have only, the only indices we'll have are either SU4 or SU2. That's it. And we will not have SO6 anymore. SO6 is just, well, we'll sometimes still use SO6 notation, but it's mostly transient. We are on our way to just having SU4 and SU2. So,
yeah, just another comment about the groups. So you mean it's not even like in SO3 and SU2, where SU2 is the double covering of SO3?
No, I think here there is no such thing. I think here these are really equal. I think that there are no such doubles, whatever.
And
I think, but someone that knows better might correct me. But I think no, here it's exactly equal. Here are two S's here, one S here. I suspect maybe here there is a, no, I think no, it's okay. No, I think these are correct equalities, yeah.
And is it like a general pattern, the fact that you have like SU2 and SO3, and then you multiply by 2, and you have SU4 and SO6?
No, I think
Is it like a general
there are these relations that I wrote. There is the one you said, SU2 is SO3, but there is a Z2 that you mod out. I think maybe they are the only ones.
Okay,
It's special. Yeah, I think those are the only ones.
Because basically the fastest way to check is to list all the dimensions of the...
Yeah, the dimensions at least need to agree. That's necessary for sure. It might not be sufficient. Yeah.
I was just wondering if there's an easy way to see why having n branes, you get like a UN symmetry rather than like, you can imagine a different group like SON or SPN or something.
Right. It could not be SON because if you had SON, the two endpoints would be on equal footing. There would be no arrows to connect the endpoints. The fact that the endpoints are charged and that there is an arrow from one endpoint of the other of the open string tells you it must be something like SUN. Why precisely SUN and why when you descend down?
Or is it UN?
So it depends. So you see that if you have this low energy physics and you have a stack of branes, how much energy does it cost to move everyone to the left? I have my stack of branes, I take a configuration, and I have the same configuration here. What's the difference in energy between these two configurations? What would you say? 0, right? It's the same thing. Just translate, no problem, right? So that overall, that trivial shift is the U1 that differs SUN and UN. So it depends. If you hold fixed one of the branes so that you break this symmetry, then it will be SUN. If you keep all the branes and allow them to move, there will be a U1 that corresponds to just moving everyone, and that's a boring U1. That's the difference between UN and SUN. But let's ignore that subtlety of the zero mode. We see that we get a theory where gluons have these endpoints, and therefore it looks like the non-abelian gauge theory, but we would have to see that we get exactly the non-abelian gauge theory with the couplings and so on. And that's a complicated business that requires studying string theory. It's not trivial.
I was just going to say about the group stuff. I think SO4 is actually double covered by SU2 times SU2, because then SO4 itself double covers SO3 times SO3. I'm less sure about the SO6 than SU4, but I think they might be different because one might be simply connected. I think the special unitary one. And then on the topic of the exceptional isomorphisms, you can just see them from the Lie algebra incompatibilities, at least up to all the finite group chunk.
Yeah, good points. Yeah, Justin is right, yeah, of course. Okay. About our second part, I agree completely. I'm still convinced there is no double cover here, but I might be wrong. We can check later. If you have a solid argument, I'll trust you more than me. Okay, let's take how many minutes break, gang? 5 minutes? Yeah, okay, 5. So when the pointer is at 7, the big one, we start again. That indeed, if you have this spinner in 10 dimensions, it's convenient to break it into 8 plus 8 components. Here is the spinner index. Here is an SU4 index. And the proof is this equality, and a similar equality for sigma m with index up. If you want the brute force proof that this is a clever way to do. And the statement is that when you decompose psi a into this plus this, and then you ask for what are the components A and B, where A can be alpha A or can be A alpha dot. You have 4 terms, this with this, this with this guy with this, and so on, right? When you contract A and B. And it turns out that these 10-dimensional matrices, they break into a 4-dimensional part and a 6-dimensional part like this, such that when you contract with this guy, so this one, for example, alpha A with just alpha A would, this guy with this guy would start giving you, so alpha with alpha would give you, say, this term down here, when index m is m. And so let's digest a little bit this decomposition. So here you see that you have indices that can be A or B, can be up or down. If both are up, it's here. If both are down, it's here. And if one is up and one is down, it's these terms here. And similarly, well, when one is up, one is down, you have one alpha dot. That's the first term. When both are down, you have 2 alphas. When both are up, you have 2 alpha dots. That's the last term. Right? So you see that the indices work out. And what this tells you is that these 10-dimensional matrices, these matrices in 10 dimensions that are 16 by 16 dimensional matrices, you can break them apart in this way. So what are the objects that are appearing here? This index A is a fundamental. This A is a anti-fundamental. So delta AB is something okay to write. Right? Delta AB I'm allowed to write. Then I have this matrix, sigma mu with index alpha and beta dot. That's the usual matrix that we use to convert a vector index into a bispinner index. So that's how I transform a vector index into a bispinner object. This I think you learned, right? When you studied at Lawrence, you can write as SU2 times SU2. When you have these indices of Lawrence that are 2-component indices, you raise them with epsilon symbols, right? So if you can lower and raise with an epsilon symbol. So epsilon A up or down is just lowering or raising with an epsilon symbol for SU2. Right? So that's what we do for SU2. Right? Then we have here new objects that you have probably never encountered before. The sigma m AB, it's the counterpart in 6 dimensions of the sigma mu alpha beta dot. Now, here, sigma mu alpha beta dot, alpha is spinner, beta is a spinner. They are in different representations. And so this sigma matrix, alpha and beta dot, they are independent a priori. Here, this sigma MAB, this matrix is symmetric in A and B. whereas here it's not. So here you have 4 degrees of freedom, and you have 2 times 2 is 4. Here you have 6 degrees of freedom, and in this index A and B, they take 4 values, but they are symmetric. So there are 4 times 3 over 2 components. Right? And so 6 equals 6. Right? So it works because these matrix sigmas are symmetric. And this is a way of going from SO4 to SU2 times SU2. This is a way of going from SO6 to SU4. Just SU4, not SU4 times SU8, just SU4. Right? So this is the translation, how I convert things from SO6 indices to SU4 indices, if I want.
Sorry, question.
Yeah.
I just want to make sure those are both fundamental indices, not like a fundamental anti-fundamental pair, or does that matter?
It very much matters. So they need to be both fundamental or both anti-fundamental. In this case, I wrote both anti-fundamental.
Both anti, okay, yeah.
But raising 2 indices, it's trivial in SU4. You just multiply by the fully antisymmetric tensor. So both antisymmetric and both symmetric are trivially related to each other. Or if you have 3 fundamentals, it's the same as 1 anti-fundamental. Right? And so you raise with the fully antisymmetric epsilon symbol, Levi-Civita. But it's crucial that it's fundamental, right? So it's crucial that it's the same type. Otherwise, it will not make sense to say it's symmetric in A and B. And so this object, everything here is allowed. It's legal from group theory point of view. It's all invariant tensors. All the indices are properly placed. And now you just take this object. You write the trivial D slash using these gamma matrices. And you ask what it becomes for the fermions. And it opens up into these 3 terms. Here I forgot some d mu. Right, and so the fermion, when you open up, you generate 3 couplings, and now everything here is 4-dimensional. It's true that there are flavor indices that are of SO6 and of SU4, which are the same. You could convert everyone to SO4 SU4 if you want, but now everyone here is in 4 dimensions, and I put again the coupling outside here. So I remove the coupling here. I put I instead of IG, and I put the coupling outside.
To construct that sigma, you said it's some kind of product between the two sides, right?
This sigma?
Yeah. How did we construct that?
So this sigma you can in 10D or
yeah, maybe means
in 10D you just need to find these Clifford algebra elements, right? So you have that the antisymmetric product of sigma m sigma n must give eta mn. Then you just find some representative of this matrix.
Yeah, but here we have split them specially in like.
Yeah, here we wrote it in a way that it's very well designed to then take the reduction from 10 to 4 dimensions.
Yeah, you were telling about the indices matching, where if you multiply psi a with psi a, if both the alphas, it could be like if you look at alpha
yeah.
and alpha dot.
Okay. So let me rewrite. So, do you agree with this equation, or does it?
It can make sense.
Hey, very trivial question. Is it this thing you call the gamma here, not call it the sigma?
Gammas and sigmas are the same thing. Where did I wrote gammas?
At the very beginning, you say there is this trace f square and a trace psi bar psi, and then there's a gamma in there.
Yeah. Gammas or sigmas. Gammas and sigmas are the same thing for me. Yeah. Yeah. Prefer. Yeah, these are the same matrices. Was this the question? No. Anyway, so this you are okay with, right? So now what it means is that when you construct psi A, gamma, AB, psi B, right? You have to open up and write 4 terms. One of them is, for example, let me write one of them. The first one, psi alpha A, gamma alpha beta, psi beta B. And so this gamma here needs to have indices alpha A and beta B to receive this guy. So I look, where is this term here? It's this one here, right? That has index alpha and beta and A and B. And so this is the guy that I would use to contract with 2 of this. And if I want to contract with 2 of this, I use this object here and so on. So it's just telling you, if you decompose this into the first components and last components, then you make a 4x4 block, and then these 4 terms would go in the respective blocks. Okay. Now, let's now let's go back to our page, I think. Let me check what are the next formulas there, but I think I want to go back to this page now. Yeah, I think this is a good point. So now we have this theory. And we will show soon that n equals 4 is conformal. For now, what we know for sure is that it's classically conformal. That we know for sure. But we will show that it's really conformal soon. And so, already at the classical level, we can write here, for this theory, the conformal algebra. Well, that we discussed already. Now, this theory has supersymmetry plus supersymmetry, and that's n equals 4 supersymmetry, because there's a lot of supersymmetry. This supersymmetry is what? Is what would reduce from this n equals 1 when I reduce to 4 dimensions, right? And now I have transformations of supersymmetry. But now I have 2 types of transformations. I can do special conformal transformations, it's one thing. Transforming fermions into bosons is another totally different thing. But now I can mix them together, right? And when I mix them together, they don't close, they form a bigger group. So the closure of these 2 guys, they lead to what's called the super conformal algebra. So that's an algebra that combines supersymmetry together with conformal transformations. And everything that I get when I take these 2 algebras and start commuting them to the generators together and seeing until it closes. Okay. So let's look at these formulas now in the page, where we see all these commutators till the end of the first page are the commutation relation of the other transformation. Okay. So let's take one generator at random, like say this Q, the first one that appears in the first equation, Q alpha A. So this is one operator. Now, what this operator would do, or maybe I'm not sure if I like this one. Okay, this one is okay. Yeah. Okay. So this operator here this is what's called a SUSY charge, or a superconformal operator. And it will transform bosons into fermions and fermions into bosons, like the transformation of n equals 1 that I wrote above. And I'm going to write explicitly its action in a little bit. But for now, I won't write it now. But then to write it now, it's more useful to explain, to do something that related to what Anna was asking. we have this SO6 and SU4 indices, right? So it's very convenient to go, like we said, mu you replace by alpha, alpha dot, and m you replace by a and b. And then all you have at the end of the day are these types of indices, alpha and alpha dots and a and b. Then everything becomes nicer, right? Like take one of these ugly terms here, for example, this one. This one, what would it become? It would just, let's write this term here, the next to the last term there. So it would be something like this. Example. The next to the last term would become much nicer. It would become minus I over 2, trace, and then look what we have. We have psi alpha A, that's okay. Then the sigma matrix M just transforms the index of phi into phi AB. So I just have commutator of phi AB. And then the epsilon symbol just raises the index of psi with psi alpha B. So you see, much nicer, much simpler than what is there, right? If I now know how to raise and lower and convert things, I get rid, and I never have sigma stuff anymore. But now, the fundamental type of objects that I have are this object, this object, this object. There will also be the, if I want gauge invariant operators, there will also be covariant derivatives, d mu, that I just convert to d alpha alpha dot, right? And finally, there is f mu nu. And you know that f mu nu, when you convert into indices alpha and alpha dot, becomes f alpha beta plus f bar alpha dot beta dot. Is it okay? So where these guys now are symmetric. I can define this object and this object. I ask, yeah, okay. When you decompose into alpha and alpha dot, you see that it splits like this. Now, then at the end of the day, all my fields, if I make a list of all my fields, I can write all of them in these indices. So now let's list all possible fundamental fields. For example, I can take my f and I can act on the f with many covariant derivatives, d to the k. More explicitly, what we mean by this is the following. I have derivative with index alpha 1, alpha dot 1, dot dot dot, derivative with index alpha k, alpha dot k, acting on f, which has indices alpha beta. This is an example of a field, fundamental field that I have in n equals 4. Now, this field, I will use the following notation to indicate this field. I will think of this field as saying, it's just notation. There is a vacuum, and I create the indices. That's what I want to do. I want to think like this. There's the vacuum, and I create the indices. So let's create the indices. Let's say there is a creation operator, b dagger, that inserts index alpha 1 dot, 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 b with index alpha k dot, dagger. So this creates the indices alpha 1 dot up to alpha k dot. And then I create the indices a dagger alpha 1 dot, 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 a dagger alpha k, but I also create a dagger alpha and A dagger beta. And so I think of my operator, d to the k of f. I think of it as I create A dagger k plus 2 indices of type alpha, and then I create k indices of type alpha dots, and this acts on the vacuum. So this is a compact notation to indicate the indices of this object. Where these guys, A dagger and B dagger, are bosonic creation operators that obey an algebra A dagger alpha, A beta equal to epsilon alpha. And similarly for B. Do you agree with this? This is just, or do you agree? I mean, do you understand this? It is just a notation to indicate one fundamental field. Now, let's see why this is very convenient. Because now, consider an object. This object has two indices alpha, right? This F. Now, who is the object that has one index, one Lorentz index only? The spinner. So let's think about psi. And we could act with k covariant derivatives on psi. Right? So what do we need? How many Lorentz index like A we need? A dagger to what power? How many alpha indices we need? We need k from the derivatives plus 1 from psi. Maybe I'll put, let me maybe put here alpha. No, I don't want. The Lorentz indices are omitted, but let me put the index A here explicitly. So the Lorentz, there is an alpha here that I'm omitting, like I'm omitting the indices of the derivatives. So there is k plus 1 here. B dagger, okay? Right? But now I need to create an SU4 index. Okay, so I create an SU4 index by putting this C dagger A here, acting on the vacuum. Where this C will be a fermionic creation operator that obeys these relations with anti-commutator that is delta AB. So these guys are fermionic, and these ones are bosonic. A and B. So you see that for each field and its derivatives, I can construct a similar object. Let's just finish. If I have an object with 0 Lorentz index, like the scalar phi AB, I said something wrong. Okay, let me write this equation, and then you can complain about something I said wrong. Let's see. How many A indices we need? A dagger to the K. How many B indices? B dagger to the K. Now we need to create two SU4 indices. So C dagger A, C dagger B acting on vacuum. So now you see that these guys are fermions. So they are antisymmetric. And there are 4 options here. So 3 options here, right? And so there are 6 options in total, right? 4 times 3 over 2. So I said before symmetric, right? I said that some object was symmetric. It was antisymmetric, of course. So let me correct that. Antisymmetric. Right? It's antisymmetric that you have 6 components. If it was symmetric, you would have 10 components. Right? Okay, perfect. What about now the object? Now we have psi, which has an index C, right? which has an index A upstairs, psi bar, which has an index A upstairs. But I can write the index A upstairs to be more consistent, to follow the pattern here. What could I do instead of putting an A upstairs?
3 downstairs.
3 downstairs, so it's more convenient to put A, B, C. Do you agree? All I'm doing is just lowering 1 in step to 3 with the epsilon tensor. Again, D to the K. And then this, what would I need to do? I would need A dagger to the K. Then I need B dagger to what power?
Again, K?
No, almost, but don't forget, I'm omitting the Lorentz index. Right? Here there is an extra alpha, here there's nothing, and here there is an alpha dot, right? So K plus 1, right? And then C dagger A, C dagger B, C dagger C, acting on the vacuum. And finally, and that's the last field you could have dk acting on the field strength F bar. The other one, and that one you would identify as A dagger to the K, B dagger to the K plus 2, and then C dagger A, C dagger B, C dagger C, C dagger D acting on the vacuum, where you see that this combination, it looks a bit, why did we put it? It's a singlet, right? Because we are putting 4, so putting them or not putting is a question of notation. And I'm putting because this notation is the most convenient one that will lead to very clean equations for the conformal transformations. Right? So from the point of view of notation, if all I cared was a mnemonic to save the fields into this notation, it looks strange. Why do I put this? This is here so that the equations I'm going to write now about how the symmetry generators act on fields so that they become reasonable. But you agree, this is a singlet, right? Because C squared is 0. So this needs to be index 1, 2, 3, 4. This is proportional to the epsilon A, B, C, D. Okay, so now you see how nice it is that each field is just a vacuum acted by some creation operators. So how do I transform a field from a list, to one field to another field? I just remove some operators and put of another type. Right? If I want to go from this guy to this guy, I just remove an A and put a C. Right? And so I could imagine now an object Q that, say, removes an index A and puts an index alpha. And this is indeed what this supersymmetry is. Then you would have Q bar, which has A and alpha dot. That would put an index alpha dot and here it would create as well an index A. Etc. And we can write a few more generators in a second. So let's just see what these generators do, what they do. So this one, for example, here, it would, for example, Q acting on a scalar would give what? Schematically, without caring much. So Q removes an index A, puts an index alpha. Would give a Fermi. Right? What would be, say, Q acting on F bar? You go to the F bar, is the last one, it has 4 C's, you remove 1 C. So now you have 3 C's, which is psi bar. right? And but not exactly. I should get derivative of psi bar, right? So I remove a c, so the c is okay, right? And I put, what did I write there? I put a b, right? I put an a, good. So I start with this, and I have one, and I put an a. I have k plus 1 and k plus 2, not k and k plus 1. So I have one extra derivative. And so this would give me derivative of psi. By the way, were you careful here? Was it psi or what was derivative of psi? It was psi, right? Here you were careful, but not in the second one. Okay. Now, should we finish, gang?
No, I have to pick up Robert. You can do whatever.
Can continue forever?
Unless you need to rebel, if you can continue forever.
Okay. Very good. So I want to reach. I want to advance a little bit more so that we reach a good punchline. But let's just look at these equations for now. So Q on phi gives psi. Q on psi bar gives derivative of psi bar. So what's the dimension of phi? 1, right? In 4 dimensions. What's the dimension of a fermion in 4 dimensions? 3/2. By how much? What happened when we acted with Q? Dimension increased by half. So from here to here, delta went to delta plus 1/2. What about here? F, field strength, dimension 2. And the psi 3/2, we said. 3/2 plus 1, 5/2. What happened from here to here? Increased by 1/2 again, right? So we see that from first to second column, delta increases by 1/2. So let's look at the page and see that that's precisely what we see in equation 1.5. That these supersymmetry transformations, Q, you see that when you act with Q, there is a minus I over 2 times Q. Remember the very first equation, when you commute with P, you get minus I times P. So P was increasing by 1, Q is increasing by 1/2. So that's what equation 1.5 is telling us. Right? Now, let's look a little bit at the other equations above 1.5. Above 1.5, the first one is Q with Q tilde gives P. Gives a translation. So that means that, first of all, if you look there, you see that that all the indices are correct. You see that if you increase the dimension by 1/2 twice, you increase the dimension by 1. So it should be a bosonic operator that increases the dimension by 1, but that was only P. Right? That was the object we saw before. So it had to be P, and then you work out the rest by just working out the indices correctly. Notice also that you could write that relation there as just a statement that Q alpha A, Q B alpha dot is equal to delta BA times momentum P alpha alpha dot. This will be much nicer without the gamma matrices, right? Without the sigma matrix. That was the purpose of going to this alpha and alpha dot, so that we don't need to have gamma matrices everywhere. And so this would have been a much nicer way of writing the first equation, right? You would say it must be a bosonic generator. It increased dimension by 1, so it's P alpha alpha dot. And then to make sure the indices work, I need to put a delta function, AV. Notice also that you also see that that's working if you come from n equals 1 supersymmetry. Let's check what happens when you do n equals 1 supersymmetry. If you do first a transformation A, you get psi. And now psi goes to basically derivative of A, roughly speaking. And so indeed, after you do 2 transformations, you get a derivative, you get a momentum translation. And if you do the opposite, if you first start with A, you get F. Now instead of F, you have A, you transform it, you put there psi, so you get derivative of psi. And so after you do twice, psi goes to derivative of psi. All right, so we see that it had to work more or less like that, and here we see explicitly in the first relation. Then the second equation, Q with Q equals Q tilde with Q tilde equals 0. Now let's think a little bit. So Q increases dimension by 1/2, right? And so Q with Q would have to be an object that increases dimension by 1. But with both indices alpha and both indices, yeah, here he wrote alpha, and alpha it should be alpha and beta, and then alpha dot should be alpha dot, beta dot. But there's no object with 2 indices of type alpha or 2 indices of type alpha dot that increases the dimension by 1, which is bosonic. So it had to be 0 on the right hand side. There was no candidate to put there. Now, let's look at the other equations. What the other equations are telling us? That momentum commutes with the supersymmetry transformation. So it tells us that we can do the transformations and then do a translation, or do the translation and then do the momentum. Or, yeah, that's basically, I don't think there's much more with it. What about the second equation in the second line? Commutator of M with Q. What would be the interpretation of this equation? Along the lines of what we said before, of M with a vector. Maybe let me continue asking, putting you on the spot. So, what's your name? Alex? I was going in like this, back. I'm not sure I'm going back so much.
What other group do you want me to look at?
The second one in the second line. M with Q.
Is that 1.7?
It's above 1.5 in the middle. The second line above 1.5. M with Q equal to I whatever times Q. How would you think you should think of this equation?
Okay, so you have a rotation, and then you have a conformal transformation, and you wind up with just some other conformal transformation.
Right. So you have a rotation acting on a supersymmetry transformation, and you get the supersymmetry transformation again. But remember, how did we argue that M with P was correct? We said that P transforms as a vector. So this equation would be the statement of what? Transforming as what?
Sorry, it's been a very long day.
No problem. This is just a statement. So M applied on something rotates that something, right?
Yep.
So this is just saying that Q rotates as a spinner. And the last equation is that Q tilde also rotates well as a spinner. Yeah.
Is it really just as simple as a spin S object has 2 S terms in general?
A spin
S object
S
has 2 S terms.
object has 2 S terms.
I guess it's 10 dimensions, so it's not really.
S or 2S plus 1? Sorry. This guy has spin 1/2, so it has 1 term. Vector would have spin 1.
2 terms.
2 terms. Yeah, it's true. It's true. It's true.
We can also see that Q raises delta by half, whereas M commuted with P. So M does not change the scale. Like in the previous case, we said that Q and Q both raised by 1.
Yeah.
So therefore, both raised by half. So we must have P on
Yes.
the right hand side.
Yes.
Here we have Q raising by half, but
But M doesn't raise, so it's better be, yes, the right hand side had to be Q, and then the indices you work out is the only thing you could write. Very good. Now, 1.6 is not an equality if you want, or you can say it's an equality, but I would say it's a definition of this S tilde and S. So now, this is what we said. We have supersymmetry transformations, we have conformal transformations, so we can do one after the other, and we get a new object. Right? If I do a special conformal and a supersymmetry transformation, if I commute Q with a special conformal, I get S tilde. And if I commute Q tilde with a special conformal, I get S. These objects, S and S tilde, are the analog of K. If Q's are square root of momentum, these S's are square root of K. Square root in the sense that anticommutator of Q with Q gives momentum, anticommutator of S with S gives K. And indeed, that's what we see in the next line after 1.6, that S with S gives K, and then the other relations that we got 0, we get 0 as well.
these are the extra ones that don't, we need these to close the algebra.
We need this to close the algebra. Now, S decreases dimension by 1/2. Okay? And so it obeys an equation like equation 1.5. What would be the difference if we replace those Q's in 1.5 by S's? plus sign instead of minus I over 2. They will tell us that S have dimension that decreases. They are the conjugate of each other, like P and K are conjugate of each other.
Can you just write the S in terms of these A and C?
We can. Yeah, indeed. So this action, this is the action of Q's on this guy. And S would be like this. So S A alpha would be something like minus I. So it creates an index A. It annihilates an index alpha. By this A with alpha downstairs, I mean I can put A gamma, epsilon alpha gamma if you prefer. But that's what it means to put downstairs, right? So I don't need to do it. An S bar, which has index alpha dot A, would be minus I. It would annihilate index A, and it would create index alpha dot. Where again? Sorry, alpha dot downstairs. Is it okay? So this is how these fields and all generators look basically like this. So all generators of supersymmetry in this type of oscillator notation, they are all bilinears of oscillators like this. Right? So for example, imagine you have an SU2 rotation, SU2 being the alpha part of the Lorentz group, right? What will it do? It will be an operator like this, where it will have A and A dagger. Right? It takes out an index and puts another index of type alpha and beta. Okay? Now, yeah, so let's conclude with this. Yeah, actually, the generators are written in the next page, actually, in 2.3. If you want to see them all. They are all written there, and 2.2 is what I just wrote there in the blackboard, and 2.1 is the precise definition of F and F bar. And so 2.1, 2.2, and 2.3 are what we went over. So let's just finish the first page. So the first page, we have the anti-commutation relation of Q's and S's. Finally, the last one that we have is 1.7. This 1.7 is again one that looks much nicer if we were to use this notation that we are using now with let's write, for example, the first equation in 1.7. I can write it here. The first equation in 1.7. What would be the right-hand side? So we would have Q alpha A S B beta. And I want to write it with this new notation. So it would be something like this. Minus I. So epsilon alpha beta, I'm okay. But this I and J are like M and N. They are SO6 indices that go from 1 to 6. All this is doing is converting this to some R AB, where this is just a rotation that just rotates the SU4 indices instead of the SO6 indices. All this sigma matrix is just making this more complicated than it needs to be. And the other one plus the other one is just delta AB, and then here there would be some rotation M within X alpha beta. Instead of all those sigma matrices contracting, etc., it would just be the rotation of the SU2. And then the other one is the same, minus a half of delta alpha beta delta AB times the dilatation operator. I think if I do it carefully, there is a factor. I think there is a 1/2 here. If we convert it carefully. And so this would be this transformation 1.7.
The epsilons contract with, how do we contract the M with gamma? I got it. Usually we use the totally antisymmetric to raise or lower things, right?
That's right. So M now, instead of M mu nu, we now have an M that rotates alpha and beta, and an M bar that rotates alpha dot and beta dot. Right? So rotating this and this is the same as rotating the mu nu indices, right? So when you act with indices just alpha, you just use this. When you act with indices alpha dot, you use this M dot. And these sigmas are such that they just give exactly this. And so, just to conclude, and tomorrow we'll pick up from here. I think this is probably a good point to stop. So we found this superconformal algebra in 4 dimensions. We have these operators that move the transform fields into each other, and there is this supersymmetry. And we have these generators Q and S. Q increases dimension by 1/2, S decreases dimension by 1/2. Because S decreases dimension, there must be an operator that you cannot decrease anymore. Like K. K decreases the dimension, and then you have the primaries where you cannot go anymore. Right? And the S is like square root of K. And so now in supersymmetry, we can define the last equation in that page, which is the superconformal primary, or the superprimary, which is the operators that are killed by S, by the S's. Right? So you start with those, and then you can increase and get the descendants and the super descendants by acting with Q's and momentum, the raising operators. And then whenever you have some operator that has some dimension delta, it comes together with a full infinite dimensional representation, which is you take that operator that is a superconformal primary, and you can act with that operator with all the generators of the conformal group to build an infinite dimensional representation. Why infinite dimensional? Because you can act as many times with momenta as you want, as many times as derivatives as you want. Right? And so each operator comes together with a family, not only the descendants that we studied already when we found the conformal blocks, but the super descendants as well, acting on this operator with all the S's and Q's and so on. And it's an infinite dimensional representation. What we will show tomorrow is the following. So let me tell you today so that I repeat tomorrow, since it's a little bit of a subtle idea. We will see that these representations, they are infinite dimensional, but in a sense, I can make sense of their dimension, because we have the operator, the primary, right? Dimension delta. And then I have the level 1, delta plus 1/2. The next level, delta plus 1. Then delta plus 3/2. And I can count how many operators there are at each level. And that there are finitely many. And so, characterizing that representation, I have levels and size of the representation at each level. And what can happen is that for some representations, the levels can be smaller than generic. What's the generic size? You start acting with Q's and P's, and it becomes bigger and bigger, and just count how many options you have. But imagine Q kills the operator. Imagine you act with Q on the operator and you get 0. That means that your representation is smaller than what it would normally be, because you start growing, but Q kills some states, and therefore the representation is smaller. And so there are the size of generic representations, they are called long, and there is the size of special representations that are called short. And they are the ones that if Q kills some operator, that operator is special and it's in the shorter representation. Now, shorter representations, when you have a short representation, you are in a short representation. You now know how you transform. So once in a short representation, you are there forever. You cannot jump from one representation to the other, right? You are in one representation, you stay there. And that means that being in a short representation is something special, that once you are there, you stay there. But being in a short representation will mean that Q will need to be 0. And by equations like this, it will mean that the dimension of that operator will be locked with the amount, with some rotation properties of that operator. So if the rotation and dilatation are tuned to have some cancellation, you must have that cancellation forever. And that will quantize the dimension of the operator. We'll say the dimension of this operator cannot move. Because, again, when you tune the dimension, if the dimension passes by a special value, it cannot move anymore if it's there, because at that value the representation is smaller. That will tell us that there are operators in our theory that can acquire quantum dimensions, but there are others that cannot. There are some operators that are really fixed and that can never get quantum dimension. Then we will go and ask, I take that operator that is, the dimension is an integer and cannot move by group theory, and I will show that by supersymmetry, that operator is related to the Lagrangian of my theory. And then I conclude that the Lagrangian of my theory has dimension 4, and that's it. And therefore, the theory is exactly conform. So that's what I wanted to do in the first half of today's lecture. So, but okay, we will finish tomorrow. So that's flashing that up will be what we are going to do. So all this will be to conclude at the very end of the day that the beta function of n equals 4 super Young Mills is 0. And the theory is just conformal at the quantum level. And for that, it's a powerful result, that, and therefore that's why we need all this powerful technology that we are developing. Okay, so see you tomorrow.